Now let's shift gears somewhat. We will explore some general forms of some of the tests we have discussed previously. These general forms will allow for the comparison of more than two groups, multiple independent variables, and the introduction of a covariate variable. These techniques have far more assumptions, complexity, and require more extensive calculations. Earlier, we discussed an independent treatment t-test for two groups. But what if the number of groups were 3 or more? This requires a more generalized test known as Anova, analysis of variance. The null statement is that the group averages are the same. The alternative statement is that at least one group is statistically different on average. This implies a post hoc analysis could be needed if we discover that the null must be rejected in order to determine exactly which groups are statistically different. The calculations for any ANOVA-related analyses are quite intense. The use of technology is highly recommended. So what are the assumptions for the ANOVA? The first 3 assumptions are grounded in the study design. You have to have continuous dependent variables. The independent variable is categorical with 2 or more independent groups. And the independence of observations is assured. The remaining 3 assumptions require further investigation. First, normality of the dependent variable. It should be noted that one-way ANOVA is considered robust to violations of normality. Thanks to the central limit theorem, we can tolerate some violation of this assumption and still attain valid results, especially at higher sample sizes. Next, no significant outliers. There should be no significant outliers in the groups of your independent variable in terms of the dependent variable. Unusual or far apart from data values compared to other data are outliers. Outliers can have a significant negative effect on our results. Because they are far away from the central tendency of the data, outliers can have a large influence on the mean of the data, and this can influence your statistical results. When sample sizes are very large, outliers tend to carry less weight due to the volume of data that can counteract or diminish the effect of the outlier. Finally, homogeneity of variances. Homogeneity of variances requires that the error variances, or residuals, be statistically the same for all groups of the independent variable. A violation of this requirement can adversely affect the type 1 error. Levine's test of equality of variances is the accepted standard for testing and assessing the equality of variances. Let's consider this example. We seek to compare the endurance scores of 4 ethnic groups. Assume alpha is 0.05. We shall assume that all assumptions have been met to run the ANOVA test. The data is presented in the left table. The top right table gives the descriptive statistics for each ethnic group. Looking at the lower right table, we see the ANOVA analysis. Note that the p-value is 0.0035, which is much smaller than 0.05. Therefore, we reject the null. At least one of these groups is statistically different than the others on average. A 2-key HSD post hoc analysis shows that Black and Asian are statistically different from each other on average. The other paired combinations are not significant. A two-way ANOVA is much like a one-way ANOVA. The assumptions are the same as those for the one-way ANOVA. The only difference is that there are 2 independent variables. As a result, we must look at the effect of each independent variable and the interaction between the two independent variables. From a hypothesis test standpoint, there are three considerations. First, two statements that deal with the statistical difference on average of the dependent variable when varying each independent variable. Last, a statement dealing with the statistical difference on average in the dependent variable that can be attributed to changes in the interaction of the two independent variables. Let's consider this example. We have an independent variable for food and a second independent variable for age. The dependent variable is the liking quotient. Let's assume that all assumptions have been met. The table on the left shows the data organized by independent variable. The results are offered in the upper right table. Notice that the p-value for food and the interaction between food and age are very small. This means that the independent variable food is significant and there is a significant interaction effect between food and age. We can further investigate to determine specifically which food selection and combinations of food with age are statistically different. We leave this analysis for another venue.